Welcome to The Explainer. Today, we're unpacking an absolute masterclass from NVIDIA CEO Jensen Huang on how artificial intelligence is fundamentally transitioning right before our eyes. You know, we're moving away from those simple text generators and basic chatbots, and we're directly entering the era of massive, reasoning token factories. So if you want to understand the architecture of the future economy, the hardware that's actually making it possible, and what this means for the digital workforce of tomorrow, well, you're in the right place. Let's get into it.
Okay, let's dive right into this incredibly bold statement from the source material. Huang states that the iPhone of tokens has arrived. But to really grasp the magnitude of what he's saying, we've got to figure out what exactly a token is and why its so-called iPhone moment changes, well, literally everything. In this new computing paradigm, a token is essentially a unit of generated intelligence. It's a distinct piece of value produced in real time. Historically, software was incredibly rigid, right? Everything was hard-coded by humans, and it just acted the exact same way every single time. But now, intelligence is being generated fluidly, right on the fly. And just like the iPhone made mobile computing wildly accessible and completely disrupted how we interact with the internet, these new AI systems are making digital reasoning scalable, dynamic, and deployable across every single industry.
Here's our roadmap for today. We're going to cover 1. Building the install base. 2. Specializing general compute. 3. AI's 4 scaling laws. 4. The agentic computing era. 5. Overcoming future bottlenecks. And 6. The new AI factory.
Section 1. Building the install base.
To really understand the foundational mechanics of the AI revolution, we actually have to start with a staggering number. $1.5 billion. That was NVIDIA's market cap after a massive historical plunge. So why did their valuation drop so drastically? Well, because to build a developer ecosystem, the company made a massive existential gamble. They decided to put CUDA, which is their specific parallel computing platform, on every single consumer GeForce chip they manufactured. This added immense production cost, completely slashed their profit margins, and basically tanked their valuation at the time. But Huang recognized a profound truth about technology. A new computing platform is completely useless without a massive install base. Developers are the lifeblood of any tech ecosystem, and developers are only going to spend their time building for platforms that can reach millions of people.
As Jensen Huang perfectly puts it, NVIDIA is the house that GeForce built. Think about it. Gamers who bought these graphics cards just to play video games were inadvertently acting as a Trojan horse. They were literally subsidizing the creation of a massive, global supercomputing network. Because CUDA was suddenly sitting on millions of ordinary gaming PCs, researchers in university labs globally had access to standardized, incredibly cheap, parallel computing power. And that massive install base is exactly what gave developers the tools they needed to kickstart the whole deep learning revolution we're experiencing today.
Section 2. Specializing general compute.
Now, once you have that massive install base, you have to build hardware systems that can actually scale up to the size of human intelligence. And the source details a really fundamental tension in hardware design. On one hand, you've got specialized accelerators. They're incredibly fast, sure, but their application domain is just far too narrow to handle varied tasks. On the other hand, you have your general-purpose computers, like a standard CPU. They can run any software and reach everyone, but they completely lack the optimized performance you need for intense tasks like AI. So how do companies balance this tension to actually stay competitive? The answer is full-stack extreme co-design. You can't just build a chip in a vacuum anymore. Companies have to design the silicon, the server systems, the networking infrastructure, and the entire software stack simultaneously. By doing the whole shebang at once, the hardware remains highly specialized and blazing fast for those intense mathematical workloads, while the software layer built on top remains flexible enough to instantly adapt to entirely new AI algorithms that didn't even exist, say, 6 months ago.
Section 3. AI's 4 scaling laws.
So with that hardware foundation totally set through extreme co-design, how exactly does the AI worker actually evolve? For years, the entire industry was effectively stuck on Phase 1 and Phase 2. Phase 1 is pre-training, which is basically feeding massive datasets into a large model so it can memorize broad patterns and just learn to mimic human language. Phase 2 is post-training, where precise human feedback refines that knowledge so the model actually behaves correctly and stays on task. But the massive transition happening right now, the one that's fundamentally shifting the global economy, is the move into Phase 3 and Phase 4. Phase 3 is test time, or inference scaling. This isn't just generating the most statistically likely next word anymore. This is the AI actually pausing to think. It runs internal simulations, reasons through complex logic, and calculates a detailed plan before it ever responds to your prompt. And finally, Phase 4 is agentic scaling. This is the big one. This is where we move completely away from a single isolated thinking model and begin spawning entire teams of specialized digital workers that collaborate with one another to solve incredibly complex multi-step problems entirely on their own.
Which brings us nicely to Section 4, the Agentic Computing Era.
This transition directly brings us to that fourth law, which will absolutely define the next decade of artificial intelligence, AI as a dedicated worker. Huang uses this fantastic analogy that just perfectly captures the shift from a pre-trained model to an independent agent. He says, if you build a highly intelligent humanoid robot to work in your kitchen, it doesn't need to literally shoot microwaves out of its fingers to heat up your food. I mean, that would be an absurd engineering feat, right? Instead, it just reads the manual, reaches out, and uses the exact same existing microwave that you use. It interacts with the world's tools the exact same way a human does.
And this is exactly how these new agentic systems, like modern open-source frameworks or specialized agent models, actually operate. They don't replace your enterprise software. They actively use it. They access your internal ground truth data, they conduct independent research on the web, and they utilize your existing digital tools. For example, an agent can autonomously open up a massive Excel spreadsheet, write a custom Python script to parse the data, analyze the long-term trends, and then directly email you a formatted summary. And if a given task is just too large for one agent, no problem. It'll spawn specialized sub-agents to divide and conquer the workload. They act exactly like highly efficient human colleagues. In fact, Huang notes that in the near future, the entity that texts you and bothers you the most at work will probably be your own AI agent, simply asking you for the next assignment because it finishes its tasks so incredibly fast.
Section 5. Overcoming future bottlenecks. But as you might guess, to fuel this massive, highly capable army of digital workers, the industry hits some major roadblocks. You simply cannot scale intelligence infinitely without running into the strict physical limitations of our world. Just a few years ago, the tech sector experienced a severe moment of panic around this very question. Are we running out of human data? Because large language models were basically devouring the entire public internet at an unprecedented rate, there was a very real mathematical limit on the horizon. The fear was that we would completely exhaust all the high-quality human-generated text, books, and articles needed for that crucial pre-training phase, which would cause AI progress to completely flatline.
But the source material reveals a truly fascinating pivot. That impending data bottleneck, it has been completely bypassed by synthetic data. This is a process where an advanced AI takes existing ground truth, deeply reasons about it, and generates vast amounts of brand new, meticulously accurate data to feed right back into its own training loop. Because we can now essentially generate infinite high-quality synthetic data, the future of AI scaling is no longer constrained by how many books or articles humans can physically write. Instead, the bottleneck is fundamentally shifted. The progress of artificial intelligence over the next decade will be entirely limited by extreme physical compute constraints, meaning how many specialized chips we can manufacture and how much raw electricity we can pump into our data centers to power them. Intelligence is now purely a function of deployed computing power.
Finally, Section 6, the new AI factory. To overcome these immense power and compute constraints, the very definition of what a data center is fundamentally changing. We're experiencing a massive transition away from old computing paradigms. Historically, a computer in a data center was essentially just a retrieval-based warehouse. A human programmer wrote an app or pre-recorded a video file, placed it on a server rack, and the computer just retrieved that file when you clicked a link. That era relied heavily on networking and vast amounts of cold storage. But new computing is entirely different. We are building generative token factories. These systems don't just retrieve pre-recorded files. They rely on sheer, raw processing throughput to actively generate valuable, situationally aware tokens of intelligence in real time. And because they are functioning literally as factories mass-producing a highly valuable product, the focus shifts right back to that extreme co-design we talked about earlier. Every single element, from the architecture of the chip itself to the liquid cooling systems running through the racks, is intensely optimized to drive the energy cost of producing a single intelligence token down to near zero.
I'm going to leave you with this final provocative thought from our explainer today. We are rapidly entering an era where intelligence is no longer a fixed biological human constraint. It is actually becoming a scalable, manufactured commodity. So whether you work in finance, healthcare, legal services, or the creative arts, if automated factories can mass-produce reasoning, long-term planning, and intellectual labor around the clock, how does that reshape your job, your industry, and really the entire global economy at large? Thank you so much for joining me on this explainer, and definitely keep your eyes firmly on the factory floor.